Okay, welcome to this tutorial on joints and joint properties in 3DEC. My name is Jim Hazard, and I am the 3DEC product manager. So we'll start out talking about how to make joints in 3DEC models. We'll talk a little bit about properties for joints, and then we'll do a couple of examples. So there's really two ways to build models in 3DEC. Number one, and this is what we've mostly done so far, is to start with a large polygon, usually just a block, and cut it into pieces to get the desired geometry. It is also possible to create multiple smaller blocks and stick them together. This is the approach you would use if you were building something in Griddle, for example. There are a couple of examples like this in the manual, but most of the examples are using approach number one, where we use cutting logic to create the shapes that we want. Now, one thing to be aware of is that when you use the cutting logic in 3DEC, the cut must pass all the way through a block. The blocks have to end up being convex. So you can't have a joint that cuts partway through a block. However, it is possible to simulate this effect by just cutting all the way through a block and then assigning strong properties to part of it so that it can't slide or slip. In this way, you can create something that is like a joint that passes partway through a block. So the commands for cutting, the most popular command for cutting is this block cut joint set. It's called joint set. It's possible to create an actual joint set by giving some spacing. We also use this command to create single joints. And so regardless of whether you want a joint set or a single joint, you need to give the orientation, which is usually dip and dip direction, the location, which is origin, which is just a point on the plane. And so that's the minimum that you need, a dip direction, and origin. It is possible to give other ways to assign the orientation. You can give a normal instead. You could actually give 3 points, and it will figure out the orientation from that. Most commonly, you give a dip direction, and origin. If you want an actual joint set, you can also give a spacing, and it will create multiple joints. You may want to give a joint set ID. This is just an integer, so that all of the joints that it creates have the same ID, and we can use this later for assigning properties and things like that. The number, you may want to limit the number of joints that it creates when you give a spacing. This is not very common. Usually you just want to fill up the whole available range that you specified, but it is possible to do so. And the persistence is something that we don't really use anymore, but I'll talk about that a little bit more later. Useful commands related to cutting are block hide and block hide off. It is possible to hide the blocks that you don't want to cut. You just say block hide range something. This will hide some of the blocks, and it will only then cut the blocks that are not hidden. Similarly, you might want to make some cuts that just define a geometry that aren't real joints. In this case, you can join them. You can say block join, and then what happens is the contact calculations are skipped for those contacts, and they basically behave exactly as if they were joined together. So I talked about dip and dip direction. This is what that means. So the dip is just the angle of the plane downwards from horizontal. The dip direction is the trace of that dipping line on the surface, measured clockwise from north, where we assume that north is positive y. So basically, yes, it's the angle measured clockwise from positive y, and it can be a number between 0 and 360 degrees. So commands that create joints. We've seen block cut joint set. You can also give the command block cut DFN. And we'll talk about DFNs in a different section that stands for discrete fracture network. Block cut tunnel. So it's possible to define the shape of a tunnel. It doesn't have to be a circle, it could be anything. And it will cut out that shape, giving you a tunnel in 3DEC. I won't talk about that in detail now. You can look in the manual. And then there's also a keyword that says whether you want to cut it out using tangential lines or radial lines. And you can see the two different cases here. You can also cut an imported geometry. So by geometry, I mean a triangulated surface. Usually it's a DXF. So imagine importing some sort of DXF. In this example, we're showing a ellipsoid that was imported, and we can actually cut that shape out of the 3DEC model. Commonly, this is used for cutting out tunnels of interesting shapes, or possibly faults that have some curvature to them that are not perfectly planar. This is done fairly regularly. Be aware that it makes a cut for every facet of this triangulated face. So if you have a very complicated DXF that you've imported with, 500,000 faces on it, then this will create a very ugly 3DEC model. I encourage you to simplify these geometries as much as you can before you try to cut with them. Okay, so pretend you've made a cut. In this case, we've just made a single planar cut. The data structures in 3DEC look like this. For every pair of blocks, you have a contact. Okay, so any two blocks that come into contact have a single contact, shown here as a red sphere. This contact is only used to calculate the normal. You need to know the normal so you can figure out the normal stresses and normal displacements. And then consequently, you can figure out the shear displacements and the shear stresses. So this assumes that the two faces that are in contact are planar, and there's a constant normal that exists between the two blocks. So it uses the contact to calculate the normal. And then you have a series of subcontacts. So once you've zoned these blocks, obviously it fills up the blocks with zones. Every grid point of these zones, there's a corresponding subcontact. And so what you have is these multiple subcontacts on every face. And this is where the actual calculations are done for normal stress, normal force, shear stress, shear displacement, and so on. So most of the action is occurring here at these subcontacts. And what this means is you can have a variation in stress or displacement across these faces. Whereas again, the contact only stores the normal. Having these subcontacts is of course necessary because you could imagine if one of these blocks started to rotate relative to the other, you might have compression on one side and tension on the other side. If you only had one contact, we wouldn't be able to resolve that sort of effect. Okay, so that's a very brief introduction to the cutting and the data structures. I'll talk a little bit about the different joint models, constitutive models, and the properties associated with these joints. So just like we showed with the zones, there are multiple constitutive models available for the joints. And again, just like the zones, we have an elastic model, which basically means it's infinitely strong and you only need to give a stiffness. We have a traditional Mohr Coulomb model where you give a friction and cohesion and possibly a tension and dilation. And then we have these more unusual models here. I won't go into a lot of detail. You can certainly read about them in the manual. The bilinear Mohr is just Mohr Coulomb with two segments of the curve. So it actually accounts for the fact that you may have a weaker joint when you have more confinement or more normal stress. Softening Mohr, what this does is you can set it up so that the peak cohesion and friction gradually decrease to a residual cohesion and friction. So this is equivalent to the strain softening model that we saw with the zones. The same idea. There's actually a creeping joint model. So again, equivalent to some of the creeping models that you saw for the zones. You can imagine a case where you have a joint that has been loaded to some level of shear stress and then held there. There will still be some displacement over time due to creeping. And so if you use one of these creep models, you can see this time-dependent displacement. Continuously yielding is a model where the properties are sort of continuously changing as this thing is shearing. You will have to read about this in the manual. It's a little bit more complicated. There is a lot of properties here, but it is useful if you want to try to get into the details of how a joint behavior might evolve as it's shearing. Most of the time, people are just using the regular Moore-Coulomb model, and that's what I'll mostly talk about here. As with the zones, it is also possible to define your own constitutive model for the joints. And people have actually done that. You can go to our website and see some of the joint models that people have created. For example, there's one there that has a more sophisticated softening that is related to fracture energy and things like that. It's not actually that hard to create these models. You need to know a little bit of C++, but you can start with the template that we give you, change a few things and create your own joint model, and it becomes a DLL, and you can just plug it in and use it instead of one of the built-in models, and it actually works pretty well. Okay, so for the rest of this section, I'm just going to talk about Moore-Coulomb behavior, because that is the one that is certainly most commonly used. So imagine you're loading up a joint in shear. There's some shear stress versus some shear displacement. You have to specify a shear stiffness. So before this thing ever starts sliding, there is still some deformation in shear related to this shear stiffness. This line is usually pretty steep. The shear stiffness is usually a fairly large number. So what happens is you get this elastic component where you start shearing it. The shear stress starts to increase with a slope related to the shear stiffness. Eventually, you reach the peak strength. The peak strength is given, of course, by the cohesion and the friction angle. The peak strength is calculated using the normal stress. So the peak strength in shear is just cohesion plus the normal stress times the tangent of the friction angle. If the shear stress hits this thing fails. What happens after failure depends on the residual properties. By default, the residual cohesion is 0. So if you specify some cohesion to this thing, and you don't specify a residual cohesion, it defaults to 0. And what you'll see is a weakening behavior here. So you'll see an instantaneous drop in strength from some peak strength to some residual strength, because by default, the residual cohesion is 0. By default, the residual friction is equal to the peak friction. So imagine a case where you did not have cohesion and you only had friction. This would load up, it would hit the peak strength, and it would continue on at the same as the peak strength, so it would be equivalent to an elastic perfectly plastic. If you want to have this sort of brittle behavior that occurs after the peak, you need to specify a different residual friction. Okay, so the parameters here are cohesion and friction angle to give you the peak strength, and potentially a residual cohesion and a residual friction angle to give you the residual strength. There's also a parameter for dilation. So you can imagine in real life, if you see a joint sliding, it can potentially ride up on top of the asperities or whatever mechanics are actually occurring there. But it's very common to see these joints open as they are sliding. And so we can give a dilation angle to account for that opening. So this is just an animation that shows you what's happening here. So imagine you have one block on top of another block. There's some constant normal stress. It starts to slide. So initially it's behaving elastically. So here's that shear stress, shear displacement curve. As soon as it reaches the the peak strength and starts to fail, you will start to see some dilation. The amount of dilation depends on the dilation angle. Let's look at the bottom plot here. So this is showing the normal displacement against shear displacement. So initially it's not dilating, it's behaving elastically. As soon as it starts to shear, it starts to open, and the amount of opening depends on that dilation angle. And now what happens is if you see a lot of shear, you can imagine you don't want to keep this joint to keep opening forever. That's not realistic. At some point, it will reach a state where it's just sliding along at some constant level of opening. And so what you want to do is give a sort of limit to the amount of dilation that can occur here. So again, it starts out elastically. There's no dilation. As soon as it starts to shear, you'll see this thing opening, and then it can reach some user-specified maximum level of dilation, and then we'll just continue on at the same amount of opening. Note that the default dilation is 0, so if you don't specify anything, it won't dilate. It will just happily slide along without dilating. Also note that the peak level of dilation is not given, and so if you don't specify anything, it will just keep on opening forever. So be aware of that. Okay, so now the question is, how do you get the joint properties? The stiffness is quite challenging. Most people do not know what the normal and shear stiffness is for the joints. Note that the units for this is stress over distance. So if you're doing metric, it's like pascals per meter or gigapascals per meter or something like that. Again, this is just some guidelines for ideas about what to choose for stiffness. To some extent, it's not super critical what you choose for the stiffness, because most of the deformation occurs after this thing starts sliding. We expect there to be a very small amount of deformation when it's not sliding. So the stiffness isn't really that critical. But you do, want to give a realistic guess here. So this is just some guideline. Imagine if you had something like a granite or a basalt. There's no alteration. There's no filling in the joint. It's just a very clean joint and a very stiff rock. The stiffness for the joints is actually quite high. It can be as much as 100 gigapascals per meter, possibly even more. Now imagine a situation where maybe you have some sort of weathering or alteration or some clay filling. You can have joints with stiffness that are significantly less than that. And here they're recommending 10 to 100 megapascals per meter. Estimating the friction is usually a little bit easier. You probably have some intuitive idea of what the friction might be. Again, it sort of depends on how clean the joint is. Top case, you might have a higher friction. In the bottom case, you might have a lower friction. This is also possible to determine using lab studies of a joint surface. It's not that hard to figure out the friction. Here's another slide on figuring out the joint stiffness. Again, maybe you don't really care about the deformation that occurs before sliding. You just want to make it more or less infinitely stiff. You don't actually want to make it really, really stiff because, as discussed before, the stiffness influences the time step. So if you make something really, really stiff, it's going to sort of mess up your time step. So there's kind of a rule of thumb in the manual here. You really don't need to make your joints more than about 10 times stiffer than the surrounding zones. Okay, so there's this little equation here. You can use this as bulk. K is bulk modulus, G is shear modulus. So, some measure of the stiffness of your zones divided by the zone size. If you take 10 times that value, you can use that for the stiffness. And then they will behave more or less like they're infinitely stiff. It's not always easy to do this calculation because you might have different properties in different zones and different zone sizes and so on. There's actually a command here, block contact compute stiffness, that will do this for you automatically. And we'll talk a little bit more about that when we do the example later. Also be aware that you don't necessarily want to make your joints too soft because then you might get a lot of overlap, which is potentially not realistic. Okay. So we've talked about properties. If you create a model and you put a bunch of cuts into it, you can then go and assign properties to the existing joints. The problem now is, what do you assign to potential new contacts that form? So look at this example here. Imagine you've got a block sliding down the hill. To start with, we have those 3 green contacts, and we can assign some properties to them. But as it's sliding down the hill, new contacts are forming. What properties do you assign to those new contacts? And here we have this concept of a material table. And I'll talk about it a little bit, and then I'll actually show an example because it makes it a little more clear. Okay, so new contacts are created when the shear displacement exceeds some length. We need to figure out a way to assign properties to the new contacts. And what we have is this command block contact, material table, default, and so on. This is a bit of a mouthful. The reason that we do this is because it's possible that you might want to have different properties when different things come into contact. So imagine you have a sandstone coming into contact with a granite. You might want to have one set of properties. And then if you have that same sandstone coming into contact with, I don't know, quartzite, you might want to have a different set of properties. And so what you end up with is a table of possible things that can come into contact and what their properties are. And this table could potentially be quite large. However, we always need to give some sort of default. So if anything comes into contact with anything, what is its properties and what is its constitutive model? The second bullet point here allows you to set different constitutive models when things come into contact. Generally, you don't need to do this. By default, it will assume that any new contacts that form will have the Moore model, the Moore Coulomb model. So you don't actually need to specify it. However, you do need to specify default properties. So this third bullet point here, block contact material table default property, you need to give at a bare minimum a normal stiffness and a shear stiffness for any new contacts that are created. This is only necessary if you're running in large strain. If you're running in small strain, we don't form new contacts, so we don't need to worry about it. In large strain, we do. All right, so let's exit out of here and just look at an example of how this works. So I've got 3DEC open here already. I'm going to open an existing project. I've given this to you in the materials that you've downloaded. So if you have the course materials, if you look in the joints directory, there's a subdirectory called material table. And there's a project there, material table.project. Okay. This is what we're doing. So model new, like usual. We're creating a single brick. We're cutting a slope into it with a dip of 35 degrees. And we're deleting the top part. Then we're going to densify it. If we haven't seen this command before, the densify command will automatically make some cuts to divide your block up into smaller pieces. So what we do is we say block densify, and we give segments in the X direction, the Y direction, and the Z direction. In this case, we want 3 segments in the X direction, 1 in the Y direction, and 1 in the Z direction. So it's basically going to chop this block up into 3 pieces. Then what we can do is assign different group names to those different 3 pieces. So we say block group base 1, if X is between -10 and -3. Block group base 2, if X is between -3 and 3. And block group base 3, if X is between 3 and 10. So if we just run lines 1 to 12, if you haven't seen this before, you can just select the lines that you want to run, right-click on them, and choose Run Selection. So I've done that. I've given you a plot here in the example. If you go look at the plot, all right, so we made one big block. We cut through it. We deleted the top part. We densified it. and then we gave different group names to these three pieces. Now, the reason we want to do that is we're going to do something like I showed in the PowerPoint, where we have a piece on top here that's going to slide down the hill. And depending on what group it hits, it's going to get different contact properties. Okay. So the trickiest part here is to make a little piece that will slide down the hill. I won't go into all the math here, but essentially I'm making a piece that has a bottom angled at 35 degrees that matches the face of the piece we just made so that it can slide down the hill. We'll do this with rigid blocks. So all we can do with rigid blocks is fix the whole block. So we fix the bottom three blocks. When they're rigid blocks, we only need to assign a density, so we don't need a stiffness. So we assign a density of 2000. Now, here's the fun part. Block contact material table, default property. We give a normal stiffness, a shear stiffness, and a friction. So any new contact that forms will get these properties. We haven't actually assigned any properties at all to anything. So as soon as we start running, and this one block is sitting on top of another block, it's going to get these properties. Now, friction is 30, and the slope is at 35 degrees. So this guy will start sliding down the slope. Contacts will form. By default, those new contacts will get a friction of 30. But let's pretend that when this guy hits base 2, remember base 2 is this green part in the middle. When it hits base 2, we want it to get different properties. Imagine maybe it was a different type of geology or something. So we can add to this material table. We've got default properties, but we now can say if there's an intersection between the group slider, which is this guy that I've made up here, and group base 2, it's going to get these properties. A normal stiffness, the shear stiffness, the same, but now the friction will be 40. So what we'll expect to see here is it will start sliding down the hill because the friction is 30. When a new contact forms between slider and base 2, the friction will be 40, and it will stop sliding because the friction is higher than the angle. All right, we turn on gravity, we turn on large strain. We can run this whole thing. And we can look at our plot. So here's our slider coming down the hill. I can just start cycling. So I can type commands interactively here in the console. So I can say model, cycle, let's say 500. All right, so that has just started sliding. And what I'm plotting on here, as well as the blocks, I'm showing vectors of displacement. And I'm also showing subcontacts. So the subcontacts are plotted as little crosses. If I hide this block, it'll be more obvious. So there's subcontacts between these other blocks, which we don't care about. There are subcontacts between the slider and the blocks underneath. And it's showing you the state. So the state is they're slipping now, right? Again, the friction is 30 degrees, slope's 35 degrees, so we expect this guy to slide down the hill. So if we cycle, now let's cycle another 1,000. All right, it keeps on sliding down the hill. Let's cycle 5,000. Here it goes, here it goes. Let's do another 5,000. Has a fun trick here. If you are in the console and you just hit the up arrow, it will execute the previous command. Actually, let's make it 10,000. Here it goes. It hits the green block. Oh, stopped running. Look, it's still cycling, but it stopped moving. Because remember in the material table, we told it if there's a contact between slider and base 2, a new contact will form and its friction will be 40 degrees. So if we hide this block, we can see that's 4 subcontacts here, but they slipped in the past. So they were slipping, but eventually it overcame its momentum and stopped slipping. And it's just sitting here on the green block. So that's how the contact material table works. Depending on what 2 things come into contact, you can assign different properties to things. At a bare minimum, you need to get a default. Okay, so that is pretty much everything I'm going to say in the PowerPoint. Now it's time to walk through an example. I've given you a PDF that walks through this example. So if you look in the material that you downloaded, there's a PDF. I encourage you to pause this video now and follow through that PDF and try to create this model yourself. It'll probably take half an hour to an hour. And then come back and we're going to talk about this model right now. Okay, so I've got, I've recently looked at this one, so I can open a recent project here. Okay, I've got the data files. I've already run this just to save time in this video. So I've got the save states. I do not have the plot, so we'll walk through making the plots. I'll walk through these data files to show you what we're doing, and then we'll make some plots. And we'll look at the results. Okay, so as always, you start with model new. The next two commands are new. We haven't seen before. Block tolerance 0.01. So when you make cuts in 3DEC, there's a built-in tolerance that prevents you from making tiny, tiny, tiny blocks, right? Imagine you try to make a cut and you're cutting off the very corner of a block such that you would end up with a little tiny, tiny piece. Often you don't want to do that. Again, having small pieces messes up your time step and they're difficult to zone and so on. So there is some built-in tolerance. I can't remember exactly what it is, some percentage of the main block size in here. Sometimes you want to make that smaller. So let's pretend you say, okay, I'm okay with having tiny blocks, or I'm okay with having smaller blocks than the default. You can actually change this by hand before you do any cutting. If you want to know what the tolerance is, let's just comment that out to start with. And let's run lines 1 to 10 here so we create a brick. If you type the command model list info, this gives you basic information about the model, including whether gravity's on and the number of cycles and so on. But if you scroll down a little bit here, you get to where the tolerances are. So ATOL is the main tolerance. By default, in this case, it's 3e-2. This is a number that's a distance. So it's an actual distance, basically 3 centimeters in this case. So we made a approximately 20 by 20 by 20 meter block, and the default tolerance is about 3 centimeters. So what that means is that if you try to make a cut, it will not make the cut if it will result in a block that's smaller than 3 centimeters. In this example, we want to allow smaller blocks than that, so we can tell it to use the tolerance of 0.01 centimeter in this case. So that's one new command. The second new command, block joined by contact on. So traditionally in 3DEC, the joining occurs block by block. And this is done because traditionally people used to run a lot of rigid block models. And if you're running a rigid block model, you need to have a contiguous block so it can work out the moment of inertia and things like that. However, what this means is contiguous blocks, and you can't have, 2 blocks stuck together with a joint cutting partway between them. So what would happen is you would join a bunch of blocks together, and then you would make a cut, and some would become unjoined in order to enforce the fact that you have these contiguous blocks. If you have a zoned model, that kind of logic isn't really necessary. We can just do the joining contact by contact. And what that means is that if I join a bunch of stuff together and I make a cut, you will not see things becoming unjoined. So we'll tell it, use this new logic so it does a joining contact by contact instead of block by block. And what that means is that things that we have previously joined will not become unjoined when we make new cuts. Okay. The rest of this so far should be familiar. We create a block, doing some cuts. So we say block cut joint set, we give a dip. If we don't specify a dip direction, it defaults to 0. In this case, it doesn't matter because the dip is 0, so it's just a horizontal plane. So we cut a horizontal plane at z equals 8.2. We hide the bottom. We cut another joint set to define the face of the slope. We hide the slope itself, and then we delete the top part. We turn off the hiding, and then we join them. So if I run everything up to line 20, and let's make a plot. So make a new plot. Let's call it blocks. I just go over to the plus and I add blocks. Right, so I have one big block. I cut this horizontal plane. I hid the bottom. I cut this slanted plane. I hid this part, deleted part that's not part of the slope, and then unhid everything. And so now I've ended up with two separate blocks that are joined together. Because I gave this block join command. So that was just creating the slope. Now I want to add the actual joints. Make this a little bit smaller so we can see the commands. I only want the joints in the slope. I don't care about the bottom part. So I hide the bottom part. And I've got 2 different joint sets. Block cut joint set, some origin with a dip of 36 degrees and a dip direction of 270. So that means it will be dipping towards the left. The spacing in this case is 1 meter. I've got another joint set dipping at 70 degrees, dip direction 160, so dipping mostly towards you. This has a spacing of 2 meters. And here I've given them different joint set IDs. This is useful if I want to give different properties to the different joint sets. In this example, I'm not doing that, but you could, in which case you've got a joint set ID associated with one joint set and a joint set ID associated with the other joint set. So again, we hid the bottom, we did the cuts. We want to turn the hiding off to bring the bottom back again. So we can run this. Okay, we can go look at our block plot. Right, now we can see these different blocks have been cut. We see these different joint sets. In general, if things are joined, it plots by, it plots in the same color. This works great. This works great if you don't use this block join by contact on command, because again, all the blocks are contiguous pieces and all the things that are joined have a single color and it all makes sense. If you're joining contact by contact, it doesn't really know how to color them, right? So we've got a contact here that's joined. This doesn't necessarily form a nice contiguous piece. So it gets a little bit confused about how to do the coloring. So when you use that block join by contact on, it's great because then the join, which we put here, does not become unjoined. But it's a little bit disconcerting when you plot the blocks by ID because it tries to plot things that it thinks are joined. If you want to see the actual IDs here, you can change the label from ID to unjoined ID. Now you can see every block has its own color. If you want to be 100% sure that we did the cutting right and the joining right, what you want to do is create a plot of the joints themselves. So I'll make a new plot here. Let's call it joints. We go to plus, and we add the joint plane. Right, so here's the actual joints. By default, they're uniform color. We can actually change it to joint set. And so now you can see the 98 set, which had the 1 meter spacing, and the 99 set, which had the 2 meter spacing. You can see here that there's no joint at the bottom because we joined it, so it's not visualized. So the joining worked. You can also see that all these joints exist. So everything here makes sense. It's possible to see one joint set at a time here. If I go down here and choose color list, I can, for example, uncheck the box for 98 and only see this joint set. Or I can do the opposite, see the other joint set. It's also useful with these 3D models. Sometimes it's a bit hard to see inside. If I reset the view back to the XZ plane, I can go here and make a cutting plane through this. So if I go to my joint plane joint set and go to cutting tool and click this little line, it actually makes a cut plane. By default, the cut plane is in the plane that you're looking at. So this is the XZ plane, and it cuts it halfway through the model. So I can see these two different joint sets here in the cut plane, and everything looks the way that I was hoping it would look. Okay, so that's just creating the blocks. Next thing we want to do is zone them. So I've got a different data file here called zone. I'm restoring the previous model. I want smaller zones in the slope. So I say, give me an edge length of 0.5 in the slope, and then give me an edge length of 2 outside of the slope. And so then I can have a more detailed model in the slope and less detailed down at the bottom where I don't care. This takes a couple of minutes to actually do the zoning. I've already got it saved here. So I'll just restore that and we can look at it. So if you create the zones and you look at your block plot, now you can see the zoning on top of the blocks. You see how they're smaller in the slope, and then they get bigger down here at the bottom. Okay, so that's the blocking and the zoning. The next thing is we need properties and boundary conditions. Again, I've got another file here called solve. Restore the zone state. I set the material properties for the rock. So I make it more Coulomb material, give it a density, IM's modulus, Poisson's ratio, cohesion and friction. This is cohesion and friction of the zones, not the joints. Block zone property, right? Now we deal with the joints. You say block contact J model assign more. So we're assigning a more Coulomb constitutive model to the joints. Remember this command where you can automatically calculate the stiffness. So we're assuming these are pretty stiff joints. It will automatically calculate the stiffness based on that equation that I showed you before. So we can run this just to see what happens. So if we run lines 1 to 12, all right, let's go look at our joints. If you click on plane joint set, you can change it from color by label to contour. And under contour, you can choose property. And under property, you can choose normal, stiffness normal. So what you can see is most of this is blue. The normal stiffness is somewhere around 5.7 E9. But there are little pieces in here that have higher stiffness than that. Because remember that equation depends on the stiffness of the surrounding zones, which in this case is constant, but it also depends on the zone size. And so where you have these cuts and you might have smaller zones, you can see here some light blue regions where they may be a little bit stiffer. Presumably somewhere in here, there are some pieces that are quite stiff. 9E10 is probably acceptable. You might have a model where you have very tiny zones and you end up with very stiff joints, which is maybe not what you want. You can actually limit the stiffness. You can set a maximum stiffness. So if you go to this this command that says contact compute stiffness, you can actually specify a maximum stiffness. I think the command is max stiff. And you can say, 1E9 or something like that. Notice also this keyword shear factor. Often people assume that the shear stiffness is less than the normal stiffness. And so you can do that here. You can say it will automatically calculate the normal stiffness according to that equation, and it will just set the shear stiffness to be 0.1 times that. And this is a common thing that people do. You can verify that that worked. If we go back to the joint plot, we hear this normal stiffness somewhere around 5.679. If I change this to stiffness shear, 5.678. So it's about 10 times less. Okay. Next thing, this is new. Let's make this font bigger. Oh. Often the joints are not 100% continuous. So the most conservative case would be to just run the model like it is now, assume that the joints have the same properties across the whole plane. That's fine. You'll get a nice conservative answer. But often you want to assign some sort of persistence to the joints so that maybe, for example, there are rock ridges and they don't have the same properties across the whole plane. We used to have a persistence keyword. Well, it still exists. There's a persistence keyword that you can use when you create the blocks, when you create the cuts, sorry. But what that does is it decides whether or not to make the cut, depending on what your persistence is. So let's say we wanted joints to be 70% persistent. When I make the cut, if I give the persistence 0.7 keyword there, every time it tries to cut a block, it will pick a random number between 0 and 1. And if the number is less than 0.7, it will make the cut. And if the number is greater than 0.7, it won't make the cut. Which is fine if you start out with 10,000 blocks and you're cutting through them and you want some of them to be cut and some of them not to be cut. But it's not fine if you only have a couple of blocks and you're making cuts, because it either decides to make the cut or not make the cut. So you end up with one giant, more or less continuous cut or a non-existent cut. And that is not what you want. What you really want is to have portions of these planes to have different properties than the other portions to account for this persistence. So this is a new command in version 9. Once you've done the zoning, you give a command like this, block contact persistence, and you give some number between 0 and 1. You give a length scale. So again, it's going to create little blobs of rock bridges according to some length scale. So in this case, we'll use 2. And what it actually does is it assigns a group name to subcontacts within these blobs, so you can give them different properties in a minute. So I say block contact persistence, 0.7, length 2. I give a name to the bridge group, and just call it bridge, so that we can run this one command here and see what happens. So it tells you down here, group bridge is assigned to 27,759 subcontacts. Because there's some randomness associated with this, you may not get exactly the persistence that you specify, but in this case, it's pretty close. The actual persistence is 0.7009, and so on. So what we can do now is go and look at the subcontacts to make sure it worked. So if we go back to our joint plot, let's plot subcontacts on top of this thing. So I go plus, I go joint subcontact. So it plots all the subcontacts and defaults to plotting them by state. And it also defaults to plotting them as a cross. I quite like looking at them as little spheres. So I can change, under the attributes, I can change the mark to sphere. By default, each sphere is 2% of the size of the whole model. That's a little bit big. You can see they're overlapping with each other. Let's change it to, 1%. Plotting them by state is not useful. We haven't actually calculated anything yet. What we want to see is the group. So we choose subcontact group. Now, what you can see here is most of them are none, so they're gray. And 30% of them have the name bridge. So these red ones are these rock bridges, and the rest of the joints are none. And so in theory, these should be little patches that are roughly 2 meters in size. And it should take up about 30% of the fault surfaces. There's some randomness to this, so they're not perfectly circular and they're not perfectly 2 meters, but on average, that's what you're getting in terms of the rock bridges. And it's a little bit hard to see here because we have 2 different joint sets. If you only want to visualize one of the joint sets, we can use the range logic with the plotting. So if I expand my subcontact plot item here, and I go to range, and right-click on that and say add range element. We can range by whatever we want, position, rectangles and spheres or group names and things like that. Let's range by the joint set. So if I double-click on joint set, by default, it's not plotting. These are the possible joint sets. 1, 2, and 3 were the joint sets that were created at the beginning when we were doing those cuts and we joined them. So we don't care about them. 98 and 99 are the true joints. So I find this not to be a little bit confusing. If I uncheck the not, now it's plotting everything, 1, 2, 3, 98, and 99. Let's pretend I only want to plot 99. So I check only 99, and it's going to plot the subcontacts only on 99 joint. I can do the same thing. So that's just for the subcontacts. I need to do the same thing for the joints themselves. If I go into the joint plane plot, and I go into range, and I right-click, and I say add range element, and I choose joint set. Again, I can uncheck the not, uncheck everything, and just leave 99. So now we see only this sort of subvertical joint set here. And again, you can see the gray is the none, and the red is the ridges. Now that we have the group names assigned, we have the ability to assign different properties to different parts of this joint. So what that looks like is if we go back to the data file, we say the property, the cohesion, the friction, cohesion of 1,000 and friction of 35 to the whole joint, right? I didn't give a range here. This is the whole joint. Then I give a higher cohesion and a higher cohesion and some tension strength to the bridges, right? So if I say range group bridge, it's going to give these properties to those red subcontacts, and the gray subcontacts will still sit with these properties. Now we'll run this in large strain. So we also need to specify what the properties are of any new contacts that might form. And remember this command, block contact material table, default property. Remember, any new contacts that form by default will be more Coulomb, so we don't have to specify that. But we do have to specify new properties. And so we're going to say normal stiffness, 1E10, shear stiffness, 1E9, friction, 35 degrees. Turn on gravity. We install in situ stresses. So if you don't remember what this command does, for every zone, it just looks at the weight of material above that zone and calculates its initial vertical stress. Same with the contacts. For every subcontact, it looks at the weight of material above that subcontact and calculates its initial vertical stress. And then you can specify the horizontal stresses as a ratio of that vertical. So in this case, we're assuming that the stress in the x direction is 0.3 times the vertical, and the stress in the y direction is 0.3 times the vertical. You fix the boundaries. You've seen this before. So we're fixing all degrees of motion on the bottom, and then the perpendicular degrees of motion on the sides. We're making 2 histories here. One is the average ratio. Remember, this is the ratio of unbalanced force to applied force. And when it solves, it's going to go down to 1E minus 5. We'll also record a history of displacement at some point on the top of the slope. We turn on large strain. And here's something we haven't seen before. Model solve elastic only. So if you recall, we did something before where we said model solve elastic. And what it did was it turned everything to be elastic, solved, then gave it its true strength, and solved again. If you say model solve elastic only, it turns everything to be elastic, it solves, turns everything back to its real strength, and stops. So in this case, we're just solving for the elastic, and we're saving it. We do this because, okay, we set some initial stresses here, but that's not going to be perfectly balanced. Because this is a slope, we're still going to need to run a bunch of cycles. There's still going to be some movement. We don't really care about that movement. I mean, this is just setting up sort of the initial stress state. What we really care about is the movement that occurs after we get to that sort of initial steady state. So if we solve only the elastic part and we save it, we can have a quick look at that. I've got it already run here. It doesn't take very long. We can go to our block plot. We can change the label to contour, and it will default to displacement. Right? You can see some displacements here, pretty small, 2 millimeters. I mean, we set it to be elastic, so there's no failure. We can add on top of here the vectors. Right? So there's some movement down the slope here, but it's not significant, really. If you want, we can look at the history. So we can add a new plot here, new plot. Let's just call it history. Go to the plus. We had a history chart. There's the ratio average, but let's look at the Z displacement. Right, so we see some downward movement, we see some bouncing, and then we see it stabilize at some relatively small amount of displacement. Right, so we solved it elastic only. Now I've got another data file here. I'm going to restore that state. And again, we don't care about the displacement so far, so we can initialize the displacements to 0. Same thing with the contacts. The contacts have a shear displacement and a normal displacement. We don't care about that. We can reset the displacements on the contacts. We also don't care about the history. So this is this initial bouncing to get to this sort of initial state. We don't care about this part of the history. We care about what happens next. I could delete the histories and then type them in again, but I'm lazy. So instead, there's this command history purge, which means it will purge the data that's being stored in the histories, but I do not have to type them in again. It's still going to record that unbalanced force ratio. It's still going to record the Z displacement. It's just getting rid of all the stuff that it's recorded already. So this is a pretty useful command when you do stuff like this. And now all I'm doing is solving. But we're not sure that this slope is going to solve. We're not sure that it's going to come to a steady state. If I just say model solve, by default, it will try to get to a ratio of 1e minus 5, but it might not get there because this slope might fail. So I can put like a safety mechanism in here. I can say model solve, ratio 1e minus 5, which is the default, or cycles 5,000. So what happens is if it doesn't reach that ratio within 5,000 steps, it will stop, and it will just save itself. So you can run this. It doesn't take that long. But just to save time, I've already run it, and I've got the save state here. I'll just restore it. Now, let's see what happened. So you will know if you actually ran it yourself that it did not reach that ratio of 1e minus 5, and it did hit the 5,000 cycle limit. So this slope is moving. If we look at the history, let's look at the history first. Wow, you can see that the Z displacement is, first of all, getting to be bigger, 1.6 centimeters, which is still not significant, but the key here is that it's still moving. If I keep on cycling, it's going to keep on moving. This is not approaching an equilibrium state. I look at the blocks, I can see displacements here. Maximum displacement is now about 10 centimeters, happening at the toes of some of these daylighting joints. You could actually plot the joints on top of this to make it clear what's happening. Let's hide the vectors for now. If I go to the plus and I plot the joints, joint planes are plotted on top here. It's a little bit hard to see them. I can make them more obvious. If I go down here in the attributes, under polygons, see there's an outline with a thickness of 1 by default. I can crank that up and make these thicker so I can see where the joints are on the surface. So it's obvious where these daylighting joints are is where we're really seeing this displacement. If you like, you can make a cut plane here. So again, I could hit reset the plot view, make a cut plane for the joints and a cut plane for the blocks. I can sort of see what's happening in a cross-section view here. Similarly for the joints, let's go look at the joints. Okay, let's turn off subcontext for now and change the joints. I click on the joint plane. I don't want to show properties anymore. I want to show shear displacement. The shear displacement is going from a minimum of 0 to a maximum of 5 centimeters. Most of the stuff is blue, so it's a bit hard to see what's happening. Let's change the contour limits here. If I go into contour, I can change the maximum to 0.01, let's say. Oh, I know what's happening here. Remember, we changed the range to show only the subvertical joints where all the action is really happening on the other joints. So you can just click on the little circle next to range and it stops using that range. Right, wow, so now we're seeing a lot of displacement on those other joint set. Let's go back and change the contour to the default. Right, so now the maximum is about 6.5 centimeters. Again, you can see a lot of motion on the toes here, which agrees with what we saw on the block plot. And again, if you really want to, you can show the cutting tool here. See the cross-section view, which is kind of cool. You could also use the subcontext to look at the state, see what's slipping, what's failed, and what's not failed. So if I turn the subcontext back on, and I change the label from subcontact group to state, where's the state? There. Now let's just look at the other joint set here. So if I go into range joint set and select 98 and unselect 99, and let's do the same with the joint planes. Turn the range back on and shows 98 and not 99. Now I can look at the state of these subcontacts here. So anything that's not gray is either slipping now or tension now, or slipping past or tension past. Let's assume we don't care about the past state here. So let's click on subcontact state. I can look at the color list. For slip past, let's change it to gray. For slip past, tension past, let's change it to gray. So now everything that is not gray is either sliding and slipping now or tension now. And that's basically almost everything, at least on these joints on the surface. So, we probably made these things too weak. All these joints are really sliding here. And they're basically ignoring those rock bridges. Again, to make this effective, we probably should have set the rock bridges to be stronger than they are. The rock bridges aren't having a big effect here. Almost all these guys are failing. These things are sliding catastrophically. This slope will not come to equilibrium. And if this was a real slope, you would have a problem. Okay, that's basically the end of this this tutorial. There are many other things we can look at with these plots, but I will leave that for you to do on your own time. I hope you enjoyed this one, and there will be more coming soon.